Alright, today I'm doing a problem that is not in the book. This is a problem that is similar to problem 9.57. So this is a good problem to practice for the test with. It's best if you try to solve it first, but if you really don't want to do that for some reason, then at least try to draw the picture and then see if we get the same thing, because a problem like this can be hard to change from words into images, so make sure you try to do that. Okay. Alright. So the book gives you the moment of inertia for a thin rectangular basically a plane. You know, it's not a plane obviously because it is in 3 dimensions, but its width, not width, but let's call it this part in here, is so thin that it basically is irrelevant for the moment of inertia. Okay. But the problem I made says that the axis of rotation is halfway along the length, right? So if this is side W, and this is side L, my problem says it's located halfway down the length of the sheet, and it's parallel to side W, as you can see. So how can we do that? Because the book only gives us the one for a sheet rotating on one end. L squared. Right? Well, what we can do is say, hey, I know that I can just split this in half and ring it up as 2. Right? That should make sense, right? Because now it's just 2 rotating on their ends. So then we would change this, call it L over 2. And this is L over 2. You can't see that. Wrote that too high. This one's L over 2. Okay. And of course, M over 2, M over 2. So we find it for 1. And then just multiply it by 2 to get the whole thing. Okay. So that wasn't that hard, because this is it. We found it. That's our answer. Because ignore the 2 for a minute. Pretend we're finding it for just this one. We have 1/3 times the mass of this, which is m over 2, times the length, which is L over 2, and W doesn't actually matter. We care about how far it gets from the axis of rotation, right? But we don't care how long it is this way, because that's just taken care of by the mass. We find all we need to know about that is how much mass is there, how far away from the center of rotation is it. That's what we care about. Okay, so 1/3 m over 2 times L squared over 2 squared, and then just multiply it for 2, and you have it for both. So that wasn't that bad. And the second one is when it's bent, right? But it doesn't say how much it's bent. And if you try to draw it, you probably were curious as to why that wasn't mentioned. That's kind of a clue, actually, because the difference between what I just had and what I'm drawing now, there is no difference as far as the moment of inertia is concerned. This is good for me because it makes me practice my 3D shape skills, drawing skills. But there is no real difference between what I just did and what I'm about to do. Because I calculated for each half separately. So if I have 2 halves and they're different in relation to each other, that means nothing to the calculation. We didn't take that into account the first time. This is sloppy. Because we just calculated them separately. It didn't matter what relation they had to each other the first time. Let's see, I need practice with this. Okay, there we go. Right, so this is still m over 2. This is still L over 2. And there's still 2 of them. So it's still this. Didn't change at all. The angle between them is irrelevant if it's still rotating, if the center of rotation is still on the end of both. So that wasn't that bad either. Third one is slightly more interesting. Okay. Third one is, after it has been bent, I should have said bent in half, pi over 2 radians, with an axis of rotation through the new center of mass. So it's been bent in half. Again. There we go. Okay. Could have just used my other drawing if I'd been thinking. But I wasn't. Okay. And I'll draw it from the top so you can see the angle between them really is 90 degrees. So that is your center of rotation right there. And it has a new axis of rotation through the center of mass of both of these. So let's see. How do we do that? Well, what's the center of mass of, ignoring this one for a second, what's the center of mass of this one? It's just halfway along. Okay, so this whole thing is L over 2 still. So that is L over 4. L over 4. Okay. So that was the axis of rotation for the old one. Excuse me. That's confusing. Okay. That was the axis of rotation for the last problem, not for this problem. So, what do we have? We have the axis of rotation through the new center of mass. And this is also L over 4. And this is L over 4. Okay. Well, we know this is 90 degrees. So if I draw a line out from here, and I draw a line out from here, and that's 90, and that's 90, then we know that this point is L over 4 away from the center of mass of each one. Think about that for a minute if that's confusing you. Because this is L over 4, this is 90 degrees, this is 90 degrees. So this is parallel to this, so this is L over 4. And so is this. So that should, hopefully that makes sense. That's your new center of mass for the bent one. Right? And it's L over 4 away from the center of mass of each part of the sheet. Now, just like in the earlier parts of this problem, we can still calculate the moment of inertia for both separately. We don't have to do them at the same time. So let's do that. It's much easier. Okay, so that's still m over 2. So we have 1/3 m over 2. And for this problem, we know we're going to have to use the parallel axis theorem, right? Which goes, the moment of inertia for this thing is going to be the moment of inertia of the center of mass plus m d squared. D squared is the distance from the center of mass to the axis of rotation. Since we're doing both separately, this is the center of mass of this one, so the distance from this center of mass to the axis of rotation is L over 4. Okay. So we need this, which is the moment of inertia for the center of mass of one sheet. Now this part can be a little confusing because we're still, excuse me, let me get rid of that. We still don't have a formula for finding the moment of inertia of a thin sheet that's rotating here. So once again, we split it into two that are rotating on their ends. So we're just finding like this slice here right now. We're finding this, the moment of inertia of that slice. So that's 1/3 times m over 4, and we're going to be multiplying that whole thing by 2 later so that we get both. So it's 2 times 1/3 times m over 4 times L over 4 squared. And that is for this whole piece. Okay. So that's one part done. That is this part here. Change that. That is that part for this. But we still need this. Okay, so plus m over 2, sorry, 1/3 m over 2 times still L over 4 squared, because L over 4 is this distance, right? Because that's what D is. D is the distance between the center of mass and the center of rotation. It's unfortunate that they're the same because that makes it confusing, but they are different pieces. Okay, but that's only that's only for half of it. So guess what we do now? Multiply a whole darn thing by 2. So that is a problem that is like 9.57. He said something like that would be on the test, so I just went ahead and made up a problem like it so that you guys would have more practice with this kind of problem. If you want to try to find more problems or make up your own problems like this, not that I think that anyone will, but I can dream. If you want to do that, then look at problems, or think of problems with a continuous mass distribution. When I say continuous mass distribution, I mean like a stick. And if you pretend that I can draw straight lines, then the mass is uniformly distributed throughout this whole thing. If the whole thing is m, then if I divide it in half, that half is m over 2. M over 4. etc. Its density and shape